This is a white sheet approach to the story of numbers as we're going to need them in operations. And some of you have had a background in math and statistics and some haven't, and some have been willfully avoiding it. And I'm trying to give an approach here that gives you the total appreciation, the total motivation, step by step, as to where we get to. And I think if you understand the motivation and the steps that are construed to give us a useful tool, then you'll have a greater appreciation. My goal for courses that I teach around operations is for everybody to leave with an appreciation of these numbers at the level that you're able to even calculate averages in your day-to-day life here, when you need to average the cost of fuel at the pump, or maybe the cost of yogurt at the store, or whatever it might be. As we watch things, there are certain phenomenon that we start paying attention to, and that's really the first step here, is noticing things. Okay, so in a primitive sense, people started just noticing the nature and relating things that were happening from day to day. And one of the most common approaches that they'd probably have is what's going on with the weather today, and especially the temperature. Okay, so we'll just focus on temperature here, where for any climb, as far as even where we live here, you can look out the windows of the mount and you can actually see the cold, blustery wind and the whiteout conditions during the winter down on the river, to people enjoying themselves generally during the summer. Now, we make assumptions here that the picture on the left is not a picture of the summer, and we make a assumption on the right that the picture is not of the winter, because we learn to expect things. And that's the nature of using these numbers, is let's just take a hunch that we have and then start applying our knowledge to this and being able to come up with useful tools for it. So the corollary to this would be, for instance, manufacturing t-shirts would be, let's look at the average weight of these t-shirts on their way out, because that affects our pricing on shipping. So I want to use a more primitive example here just to see how we built up the knowledge of numbers. Okay, so the first thing we noticed, let's say the cave people noticed, is that, hey, you know what? Over the period of a year, temperatures got warmer and colder. But there's a cycle from year to year, thank goodness, because as we headed into September and they started marking their days off on the cave wall on their calendar, and they just see the temperature as they start recording this going down and down and down and down, without the benefit of having a full year cycle. You can imagine that they're going, well, this is just going to continue down further and further and further to an ice age and a frozen earth, and we're all gone. Okay, but lo and behold, year after year, they grew to appreciate that there was some time working from one season to another, and eventually they came up with a 365-day calendar, which approximated what an average year, the length of an average year is. Of course, we have a leap year there, okay, to account for natural phenomenon. But the rough cut of this entire story is that suddenly, when they started marking this down, with every sunrise, when they marked down the temperature at the sunrise, that they started noticing that there was a pattern developing. Okay, so they needed to start measuring things. Okay, so the next natural event here was that we're going to start recording things. So you have to invent things like the scale of temperature and a thermometer, but let's assume they had that. Okay, so they start measuring things, and they were writing them down. So this is a typical cave drawing that they had on the side of the cave here, on the wall of the cave here, and over a period of, let's say 200 years, they gathered their data. And what we see on the left is the index, what year we are in, versus this temperature on this date of that year. So we're on November 11th or 12th here. Let's call it November 12th. And for every year on that date, they recorded the temperature. So we have 200 years of climate data now. And they recorded it to the 10th of the degree. And that's just a total arbitrary for the sake of our argument. Okay, so we notice a phenomenon. We find out what the characteristic of it is temperature, and we start recording it. And we're beginning to get more sophisticated, because after we started measuring things, then we started recording things, we start organizing things. So if we come over to our data here, we notice that, okay, this is great. This is one representation. It's a scale over time of, or recording over time of temperatures for a particular date. But what if we copy this over and start manipulating it? I don't want to get away from the fact that we have some original data here. I don't want to destroy the original data. Okay, and what we can do is we can say, hey, you know what? There's this other thing we invented, and that's charting. Okay, so we can look at it in tabular form, or we can look at it as a chart. So the cave people said, okay, let's draw a picture of what this data looks like. Okay, we're going to go up to top, grab this data, and we're going to chart it in a scatter diagram. Okay, so look at that. Interesting. A couple of things that we can take from the first level of summarizing data here is that we do have a range, okay? And the range was from just about 40 degrees up to something less than 70. All our data is bracketed at the low end by 40 and at the high end by 70 degrees Fahrenheit, okay? And this just shows us over time. Our x-axis here is over time, and it shows the data moving around. And what we're recording is the temperature over the last 200 years for the 12th of November. Okay, so that's really interesting. But now we can take a look to see, why don't we rearrange this? Now we're getting a little smarter about this. We're going to manipulate data. Okay, and what if we grab this data and instead of going over time on the left-hand column here, what if we sort our data according to temperature? Let's do low to high here. So we're going to sort by column B, small to high. And now if you look at it, the years, they're all scrambled now, because what we did is we drew ourselves a picture of the data. We ordered our data here from low to high. The low is at a 42.2 degrees, and the high on this date over the last 200 years was 67.2. We're learning how to manipulate the data in ways that are beneficial to us, okay? And that's part of the story here, is that's what we're going to continue doing here to get a little bit more of a sophisticated model of the data that we have. Okay, so let's graph that. Now we're going to graph something different. We're graphing from the low temp to the high temp instead of early, long ago date to present time. We're going to graph from low to high. Give ourselves another scatter diagram here. The numbers are all bunched together. And there's an interesting, what we can tell by this is that over the 200 items that we have, the range, again, we can pull out of this information. It's just above 40 here, it looks like, and something below 70 there. And these are little dots painted here. That's why it looks like there's a discontinuity here. There's a little jump from one dot to another there. But it had to do with our data. Something's interesting about this. It looks like an S, a little soft S, the behavior of this. Okay. So the next step that we did was we showed the range in temperature, what the behavior is, what's the relationship in the data manipulated so that it's from low to high here. So the next step in our approach to this, after we've lived with this for a little while, we start saying, well, how often do certain ranges of these numbers come up? Okay, and this is a big advance in our thinking, because we went from just organizing things, the raw data here, to counting things. We're counting how many times something happens. And this is a really big point. One of the big reasons why I'm doing the video is to appreciate that we have raw data organized two different ways, one of them by time and one of them by size rank, from the lowest to the highest. Okay, so we went from just taking the raw data to something where we start counting up how frequently something happens. Okay, the cave people started getting around their little fires at night and saying, gee, you know, it seems like we had a whole lot more days around. Something seems like 52 seems like a number that we had a whole bunch of days around, and then we have a few days where it's colder and a few days where it's really much warmer, but most of the time things just seem to be seems to me like 52 degrees. So let's advance our thinking here. So let's take our table. I'm going to preserve what we did there, and we're going to copy it in front of the Z table. Okay, so we have another page here, same data, but we're advancing our thinking here. Okay, So I'm going to save this off, move this up to the top a little bit, shrink it down as a footnote. All right. Okay. And what we're now going to say is, you know what, let's take a look at how frequently temperatures between certain ranges occur. Okay. So we're going to create bins. Okay. And we're going to say, the first bin is everything up to 40. How many days did, and we're counting here, how many days was it below 40 to 40? Okay. And how about, let's use 5 degrees as our bin size. So 45 degrees is the next separator. And we'll take this and we'll say, for every 5 degrees, tell me how many times we had temperatures up to 40, how many times from 40 to 45, from 45 to 50. Okay, so let's count how many times that happened. This is the big shift. This is what gets us to statistics, is we went from raw data to counting how often that happens or how frequently that happens. Okay, so we're going to go to data analysis, and the fancy term for all this is histogram. A histogram is going to be a chart or a graphic that shows us the frequency. Now we're moving into that probability or the frequency that something's going to happen. So we use the histogram. Okay, so let's create a histogram for this, and we'll do an input range of, let's make this C, and the bin range is from here to here. We have to feed the function, and we're not going to use labels, and the output range is, where do we want this to drop our information, is at H8. And we'll do cumulative percentage. What we're going to do is show the total percentage across all the bins. And oh yeah, sure, let's take a picture of that. Let's get an image of that as a chart. Okay, so those are what all those options do. Okay, you don't have to know that, just track this. Don't overthink what we just did there, but take the output. What we were trying to do is figure out, in a standard bin width of 5 degrees, how many times things happened. Again, please take this as a note. Think about this, back up, go over this again, and understand that we've shifted now from raw data to counting how many times those data appear. Remember, data is plural. Okay, so how many times do those data appear? Okay, and if we ignore the red line for a minute, what we're saying is there were no instances of temperatures up to and including or excluding 40. This is the way the function in Excel works. Okay, there were some number here of temperatures between 40 and up to, and just up to, but not including 45. Okay, and we can just pick out with that little blue bar that we see there would be the number 8. So this column here is what each of these blue towers, each of these columns originate from. Okay, so we can correlate that little blue bar is 8 high, the next one is 39 high, the next one is 70 high. Okay, so we're just counting the number of times we have temperatures in these ranges. Okay, and again, that's the big shift, because now we can say that for the range of 40 to just barely 45 or just under 45, we had 8 days. It doesn't really occur very frequently compared to the next bin where we had 39, and the next bin even had more, with 70, and the next bin had a few fewer, which was 59, and it starts dropping off again. So it increases around the middle and decreases off to the other side. Okay, and this is the nature of much data in our society, the way psychology, the way people behave. It's just a style of data or a type of data that we can compare, where things are centrally clustered around some midpoint. Okay, and to give you an example as a difference to contrast this, is there are types of data where you'll get a cluster at a high point and a low point, but nothing in between. In the extreme example of that, you'll have a spike down low and you'll have a spike high, and that's exactly the definition of quantum mechanics, where an electron can only live at two or more distinct places, one or more, but two, three, four different shells around the nucleus. That's the foundation of quantum mechanics, is that it's quantized. They only occur at certain places. And if you want to see some real strange information, is take a look at that, get into that a little bit, and there's no chance of an electron living between those two levels. And that's what the weird part of quantum mechanics is that they only live at certain levels. They just appear magically at a different level. They don't move from one or another. They talk about it shifting. But that's just to give you an example of different kinds of data. So all of what we're doing right now from here forward has to do with data that's clustered like this around the central point. So we've really moved ahead quite a bit. I mean, in society, it took people a long time to start thinking about data this way, okay? And just a little historical reference, it took a long time, millennia, before people started understanding the concept of zero, even. If sometime you want to take a look at where the foundations of math came from, the concept of zero took a long time to come around to. So we're living on the shoulders of giants that went before us, that figured this out and are going to eventually give us some tools for operations and predicting and managing to a high quality level, okay? So in this climate data, which I used somewhat accurately, okay? So this data was deliberately modeled as far as the behavior here, okay? So this is really random numbers I generated that adhere to this behavior, because so much data science is around normal data, normal distribution data, okay? All right, and we're going to talk about the behavior of this. There's a few things that we're going to notice here. But the big shift, again, is that we went from just looking at the raw data like this to considering how many points fall within certain ranges. So that's what the core of the normal distributed data story is about. The core of it is just that things tend to cluster around the middle. At the expense of possibly over-explaining this, but if you're struggling at this point, I hope you're not. I hope so far you've gathered everything in. Try to take it as it's presented, as it's just the facts. And the ability of YouTube, you're able to go forward, move back, speed it up, slow it down. You can change the speed in YouTube by going down to where the gear is. Click that. There's a little gear that means settings window, and it'll give you the settings window, and what you'll be able to do is there's a speed entry there, and you can speed it up and slow it down. I find I can listen to most videos at 2x. So whatever the length of this video shows, you can listen to it in half that time. And the big point is come back to it over and over and over again. And what you're seeing here is a refinement of the story over many classes I've taught, trying to bring the story of these numbers into perspective for students so they can succeed with this and go forward, impressing other people at work that you are among the very few that really sat down to understand what all this statistics is about. So far, so good, hopefully. Now, let's paint it in the world of operations. Okay, I want to paint what happens. We collected the data over here over a period of 200 years. Okay, I just want to make the correlate so we're clear about this. So in operations, what happens is we would have a table, and we'll say we're making motorcycle helmets, and our table starts collecting data automatically, and let's call it the weight of the motorcycle helmet. Okay, so every unit that comes off these days, it's not hard to instrument a factory, so every unit that comes off we can measure the weight of that accurately, and we're going to have some variability in there. Okay, and so you would think that if you made a motorcycle helmet that was supposed to be 2.5 kilograms, that's the end of the story. But no, okay? We live in a world where data ranges around a center point, and for many reasons inside our control and outside our control, in the instance of a motorcycle helmet factory, you might get something that instead of 2.50 kilograms is 2.59 kilograms, as you sample these things, there's going to be some kind of behavior setting up here where they range maybe only by a tenth of a kilogram, or rather a hundredth of a kilogram here, right? And the goal of the factory is to make this variance as little as possible, the variability, and we do measure things in variance and standard deviation. And however, the concept there is what you need to get here is that these will vary. So how do we accommodate that? How do we deliver the quality to a customer anyway? And just to make the corollary here, let's talk about the raw data, which I was talking about here. So we're going to collect raw data. But then we're going to have another graph on our dashboard here. We'll have, so this is one dial on our dashboard that we're reading what the latest weight of one of these helmets is. And right next to it we'll have another meter over here which will be saying what's the frequency of these numbers, okay? And what happens is at the beginning of the day, if we're just taking today's data, we're going to have no data, okay? And let's say historically, let's just make a graph here, for instance. And of course this is your X and this is your Y graph. And it seems to be that our average is going to be something like 2.50 is what we're shooting for. Okay, at this point of the discussion, let's just take that our target is 2.50 and it's the average weight of the helmet coming off the line. We're going to find out later, very shortly here, why that's not, the average is not a good target. Okay, but let's just take that for granted right now. And what happens is we start accumulating data over the day, and we want to count how many times we're getting close to 2.50. And as we go over the day, for every dot I'm going to put down here, that's the number of times that we have a helmet weighing in this bin. Okay, so again, we separate the entire scale. We decide some arbitrary measurement yardstick we're going to use along the bottom here, and let's say that this is in hundredths. Every mark here is a hundredth of a kilogram. And what we're going to do is, if we count up from 2.50 kilograms, this is 01, 02, 03, 04, 05, 06, 07, 08. Okay, so that's 2.58 kilograms up here. Okay, just to give you an idea, 1, 2, 3, 4, 5, 6, 7, 8. That's going to be 2.42 kilograms down here. And every time we find the weight falls between these range of numbers, okay, we count it, okay? And so we're keeping the raw data rolling in here. And then we're manipulating it, so we're counting how many times we get a motorcycle helmet between these two bookends of each of these bins or categories or classifications. They're very arbitrary, okay? And as over the period of the day, as the data starts showing up, I'll just put a dot down there. Every time an added dot is like the count. So this is really the count. Remember, the big shift is in counting now. And we're counting. And the nature of the data, we can tell you, is that more points will occur as we're adding these up. These little dots appear every time we get a new record in here. These we assign a dot, we add a dot, we're adding the count. The count is the Y axis here. How many do we have in this bin? And as I described, over the period of the day, we're going to get many more motorcycle helmets near our average. It's just the way the world, literally the physics of the world work, and the behavior of the world works for what we need to do, need to understand is we have far more occurrences clustered around the average. And if you painted the envelope of what this data looks like, it starts looking like the bell curve. Okay. Why I'm going into this in such great detail is get comfortable with what we're doing here. We're counting the number of occurrences. Okay, it's not the raw data, it's the number of occurrences. Same data, we're just representing it a little bit differently. And that's what we call, okay, we've called it before, we've called the bell curve, but now you've paid for the big words, and we're going to call it normally distributed data, or the normal distribution. Okay, and there's an ideal model for mathematics of what normal distribution looks like. that you're pretty much familiar with. If we painted this, I could actually plot perfect data here, and we would have a really smooth curve. Not what I'm showing here might be actual curve of what it looks like. The profile or the envelope of the counts would look kind of like this, and there's actually eventually adjustments we can make for our data not exactly fitting the ideal case, and we don't get into that in this class. But that would be an advanced class in math and in operations as to how do we account for the error in our data not matching what ideal is, the ideal smooth curve is. Okay, so again, the point for the third or fourth time is this is what we're working with in this realm. You have to be very aware of this. This is why I've made this video, why I'm going through it this slowly, is it's the world of counting, and the data that we have clusters around the center point, and all the math and science that we're going to talk about coming up has to do with this kind of data. If you have other kinds of data where the data seem to be clustered for some reason between low and high, that would be called bipolar data, where you have highs and lows around a center point, and that's just one other kind of data. There's plenty other kind of forms out there with plenty of calculus around it to use as tools for whatever, management or science or whatever it might be. Okay, now what's the next step? What we've done so far is we've got a slightly more sophisticated approach. We have two dials on a dashboard here. We have the raw data, and then we counted things. That's all we did so far. Now, the next step with this, page down here, is let's standardize things from day to day or from operation to operation. And let's say our cave people have friends over on the coast. Okay, so actually they're out there on some island, and on the mainland they get together for the statistics conference every year, the Caveman Statistics Conference every year, and what we do is start developing a language. Okay, there's two items that define the standard, rather the normal distribution. One of them is the average. I've been kind of using the term, and the average, everybody can probably calculate, is for I equals 1 to 200 points. Okay, what we do is we sum up x of I to n, where n is 200. Okay, so from I is equal to 1 to 200, we add all of these up, and then what? We just divide by the number of points. Okay, the core of understanding the next step is that the next step is just another average. Okay, it's a different kind of average that uses the first average. So this is the real true first average. The other descriptor of the data is how closely bundled to the middle of this, where the mean is or the average is of our data. How tight is the data to this? How far does it range away from this? It really was a natural question. The motivation there was when we started looking at the data, this is cave people talk, they said, you know what, this could be clustered very closely to the middle, or it might be very spread out. So we want to know the approximate middle point is your normal first average, but what's the average distance to that mean of all the points? Therein lies the biggest next step, is understanding is they take every point here and they took the distance from it to the average. Okay, now following our understanding here, if I were to draw this out, now I'll use the other side of the curve here. Okay, and what we're going to do for just this bin, see this vertical bin here, when we calculate this new average, there's going to be 200 numbers again. There'll be 200 numbers, but it's going to be every point, whatever that value is, minus the mean. That's all we're doing. For 200 times, we're just going to measure that. What you're going to end up with is another table. You can put another column right here on your table, D. Okay, and we can calculate how far away from the mean that is for every point. Now remember we clustered these together. Okay, So all these dots, if you count these dots, there would be 200 dots underneath here. Okay, that's one dot for every point. So if we measure the distance of one point that is this far away, we had 1, 2, 3 others also. So there were a total of 4 points here of the same value or within the same bin. Okay, and each of those 4 is going to have the same distance to the mean, right? So just as in there were many points around the center line here, the effective function here, where we're taking the point value minus the average, now we're just taking this distance, okay? There will be 4 numbers in that table at that distance. That weights this value by 4, okay? Just get the idea there that this is going to show up, this distance is going to show up 4 times in our distance table, okay? So let me say this very carefully again. What we are interested in is, gee, what is the shape of this curve? And let's invent this thing where we determine what's the average distance of all the points to the curve. And that's the launching pad for all statistics. Everything else is then based on this. All forward motion, take further statistics classes. Pretty much everything around this is how frequently something happens. And quite a bit of statistics is around the normal curve. Not all of it. I keep stressing that just so we don't get confused or short-sighted in all this. And the motivation here, I'll say it again, is trying to find the average distance to the mean of all the points. So there's 2 averages. We're just taking 2 averages. Mechanically, you should be able to do that now. If you go over that, you should memorize, I highly recommend you memorize, the motivation here is the average distance to the mean of all the points. And so you're going to have 200 distances in a table. So let's get on with our discussion here. We'll go back over to PowerPoint. And that was the story of standardizing things. We're standardizing our description of this curve. We're defining it by an average that we have, and we're defining it by the average distance to the mean of all the points. So there's really just, all we're going to compute is 2 different averages. That's all we're going to do. So let me copy this page again. And let me try to erase, I don't know if I can do that. I'm going to have to get another page. This is very filled up. So to continue, what I've done is I've brought in an image of the normal distribution, so it's not my handwritten version of it, but you can see where this is the perfect shape, and we had the sense that in our data, when we classified our data within 5 degrees Fahrenheit bins, the data started taking on this normal distribution look to it. Okay, so let's calculate that now. As I described before, this is pretty much straightforward, where let's calculate the average temperature of all this. Which is 53.8 degrees. And I'm going to put the double lines underneath here. We're just going to do a quick format on this. .8 is our first average, sense of the first average, and I'll flood that with yellow. That's an important cell right there. Now we're going to, that we have the first average, we have to create the second average. Okay, we give ourselves a little bit of headroom here. I need another row. Okay, and what we're going to do is start a few columns here, and we want to say, what is the distance to that mean or that average. Okay, so what we're going to do is take our number and we're going to subtract what the mean was. So we're down below the mean by 11.6 at the lowest minimum value in our range. Our range is 42 to 67, 68. So what I've done is I've brought in a perfect representation or representation of perfect data for normally distributed situation. Okay, so this is a curve. This is absolutely accurate to what a perfect normal distribution envelope looks like. It has a distinctive shape. I will explain that. What I mean by that is the curves in here are such that it's not flat at top like this, with then a kind of a flat, abrupt corner down here. Okay, there's a particular curve to this that we define with two different things. One of them has to do with the center point here, which we know is the expected value. It's called the mean or our average. Those are all three words for the same thing. So the first thing that defines this is that, and the second thing is how wide is our data or how narrow is our data. So for a set of data we can calculate something called the average distance to the mean of all the points, and we have 200 points here. Okay, and we can go ahead and calculate that. Okay, so let's look at what the average distance to the mean is. So what I've done is I've set up the table a little bit so that I've calculated the average down at the bottom here. You can see that I've put it in gold. Our average is 53.8, and I'll click on that box just so you can see I just used the function from Excel. It's the average of all those 200 points. Okay, and I want to keep having to go down there, so I'm going to bring that back up to the top, and I named it our dot average. Okay, so I'll put that in there. We'll get a name does not resolve. Okay, and what I'm going to show you is you can name cells that are important in Excel by clicking up here and type in here r dot average. Okay, and now that we named that, our name should resolve up at the top. So we notice that it's now 53.7805. Okay, I'm going to do one function to that, and that is I want to round that to just one decimal place, just to keep data clean in here. I'm not too worried about precision at this point. So it's 53.8. That's more legible, and I'll paint that yellow as well. So if we're going to do the average distance to the mean, we need the distance to the mean for every point. Okay, so what we're going to do is say that that is equal to the point of interest. What's the distance to the mean? It's that point of interest minus the mean. How far away are we? Now, one thing I want to do is make an absolute reference here. Function f4, that gives you the absolute reference to that, so that I can grab this and we can look at the distances of all the points to the mean. So for every point, we can look how far away they are. Now we still have ordered data. Our data got ordered according to size, small to large. Okay, so you're going to see that the distances are going to diminish as we come up to a certain point, and then it's going to get really close to 0. We're still negative here. If you notice, our numbers are all negative, and then in the world of our precision, we had a couple of data points that were right at the mean. So the distance from the mean is 0, and then as we move to the right of the mean, the numbers get bigger than the mean. They're all positive. Okay, so the first conundrum presents itself. If we wanted to do the average right now, the problem is that we're not using the absolute value of the distance, and all the negative numbers would negate the positive numbers, and we'd come out with the average to be approximately 0, because all the negative numbers, as I mentioned, would negate the positive numbers. So we end up with the situation where we have to apply the absolute value of it. Okay, so now this is where our story takes off, and now we need the absolute value of all these numbers. So this is going to equal this. We'll put the absolute value function in here. We'll click that and we'll close it off, and it's going to give us the positive value of these. So we're really interested in just the positive value. How far away is that point? We don't care about the plus or negative. How far away is our point from the mean? So now we have the same numbers, but they're all positive. Okay, so that was one of our issues that we had to deal with, was these negative numbers. That's the first thing. So we created this absolute value, and now we can do the average of that. So we'll grab the whole column of numbers here. And when we do that, the average distance to the mean of all the points is 4.1125. And I want to save that off and paint it yellow because it's that important. So now we have the average, and we have the average distance to the mean, and we can go to our curve over here. I'm going to grab it. I'm going to do another one over here. Okay, I'm going to save what we had there. Okay, and so what we said was our average was 50. Whoops, try that again. I grabbed the picture instead. Our average x bar is quite frequently what we use as symbology for that. X bar is equal to 53.8. And what we said was the average distance of all the points to the mean was 4.1125. So what does that mean on here? It means that some point 4.1125, let's just keep it as 4.1, that we can mark that on our x-axis. Okay, so if we go up one average, 4.1 from the mean, we would end up somewhere on this x-axis here, and in fact it would be 53.8 plus 4.1. Okay, so we just want to find out where that point, this arbitrary point, we made this thing up. This average distance to the mean is just something we made up, and so we're going to say is equal to 53.8 plus 4.1. So the place on the curve at 57.9, that we're just picking an arbitrary place on the x-axis. We're adding the average distance to the mean, average distance to mean, we'll call it ADTM, to the average. So we have an idea. We have a visual now. Okay, so all points considered, when we average those all out, those how far away they are, it's 4.11, right? This becomes our yardstick. Okay, if our data were closer to the average, they were clustered here around here, so that our curve looked something more like this, and we just go through, this is the first test question I'll ask you, is if the shape of the curve was like this instead of this, and we knew that this average distance to the mean is 4.1, you should be able to say that the average distance to the mean of all these points is a lot less than that. It could be as little as 2.05, like half of that much, right? If your curve looks like this, you'd actually have to go compute it. This is why we use this metric at all. This is the grand point of much of what we've just said, is we've come up with a metric that says how far away are most of the points. Okay, I'm saying this a lot of times in different ways, each of them correct, so that you could go through this over and over again and get down what the motivation is of why we're after these, eventually what we're going to look at as far as statistics go. Okay, so we use the cave person definition of a yardstick, and we said let's do the average distance to the mean. Okay, so one of the issues there is to put it in equation form. Okay, is we took all of our points, x of I I equal to 1, 2, n, which is 200. And we subtracted the mean. And then we took that whole thing, we added all those distances, these are the individual 200 different distances here, and we divided by 200, which is our n. Okay, so n is equal to the number of points, it's 200. And we came out with 4.1. Okay. Now, we did a little bit of a procedure in here to make sure that this came out right, and we did the absolute values of all these distances. Now, this becomes significant. All right. So in the next millennia, after the cave people were walking around to the cave people statistics conference on temperature, climate data, they had figured out that one locale might have variability in their data that's 4.1 degrees Fahrenheit. Remember that. Don't forget what our native data is. Our native data for our problem is degrees Fahrenheit. It says the average distance is 4.1. And for 1,000 years or 1,000,000 years, everybody was very happy coming with that as comparative data. So if this group lived out on the island and then another group lived on a desert or in a desert, right? If you live in a desert, what's the average? Let's use logic here. Okay, we're going to approach business problems this way with logic. And what is the average out in the Arizona deserts out there? Okay, so let's say the average, well, that's kind of difficult because actually it gets cold there at night, but let's pick, this was a fairly stable island temperature set that we had, but let's pick southeast Florida and watch its temperature because that's about the warmest place in the country sustainably. And so the average temperature in Coral Gables is 73 degrees, okay? And it's moderated by things like the Gulf Stream and other things. It doesn't get very cold. Most of the time, the temperature doesn't vary from there, and the data is very narrow, okay? And that's what we're talking about. The average distance to the mean of all the points is a lot less here. Just run the average, right? Okay, I'm spending a lot of time on this because we're going to make a left-hand turn here all of a sudden, and we need to remember this. We need to remember what our motivation was, is that if we come to the conference, whereas our data on the island varied by, on average, 4.1 degrees, here we might have 71 on the curve, 75 on the curve. Okay, so we went down 2 and up 2 degrees on the curve, and if we take all our data here, is we ended up with something like 2.02 degrees Fahrenheit is the average distance to the mean. Okay? And everyone was very happy with this for a very long time. Okay? And then this is where we make our left-hand turn, folks. Okay? Because this has all been understandable up to this point. Okay? There's just one little complication in this, and it came to do with the very smart mathematicians that worked on statistics, and they had a little problem. So where we took the absolute value of a point to the mean, we took the absolute value, the calculus of statistics and math at all, this is a very non-productive function. The absolute value of some number here, the absolute value, just the positive of it, doesn't go anywhere. There's our arrow here. It doesn't go anywhere in math. It's just a clumsy, clunky thought, and we needed to invent something better. Okay, so here comes the advanced thinking. Okay, once they got past this level of statistics, truly this is probably what happened in real life, is they started looking forward as to how do we develop further concepts around statistics. And in order to do that, this behaved not at all. And what they needed to do, and they tried this out, they kept moving it forward, moving back, moving forward, moving back. They tried different things. And there's a different function we can use to get a positive value out of that, is we can take every one of our i's, still do the subtraction here, let's just square it. The square gives us a positive number, and within that number is buried in there the knowledge of the point of interest and our average in there, right? So let's work on the calculus of statistics, similar to what we have here, And they discovered that this problem actually got wings, and they were able to develop here. This is the advancement of statistics. Now, they had to back up a few times. They kept going and going and going, and that's what developing calculus is all about, is developing a system of mathematical equations that holds true across many different situations. And then the conference would be a lot more interesting when we got together again. So that's what they were after. But what do we need to do to this? Okay, so our previous equation, if you remember, I'll rewrite it hopefully a little bit clearer here. Our original equation was x of I minus, back here. Why did it do that? Okay, I have to back up a second here. Okay. For some reason it jumps to the top whenever I undo something. Okay. I want to write this as clearly as possible. So we had the idea of x of I minus the average, and what we did is we summed all of them over the 200 that we have. You just keep plugging in the index of x of 1, x of 2, x of 3, all the way through. What is the x? All those 200 different x's, and this was a known. This is just a constant. We just kept subtracting that from all of them. And then we divided this entire thing by the number of points, and you can see that's an average. Okay, that's like that is the definition of an average. Okay, now where we're going to move to is the same similar concept to there, where we're going to go I is equal to, well, we have to get all of these points in here, and we're going to take every I, or every x of I, and subtract the mean from it. But now we said we're going to square it. Well, when we do that, we immediately end up with the intention to bookend this thing on the other side with a square root somewhere. And the math that works, you have to accept this. This is math that works. They needed to develop this so that they could go forward into calculus. What if we divide by n here? Okay, so we have the average squared value of the distances, but somewhere we have to bring this back home, and we have to do a square root somewhere with that, because this was just a function to give us a positive value. Okay, and here's something to memorize. The square root goes around everything, even the n below it. Even though the square is up here, you'll notice we don't have n squared down here. It's just n. Okay, that's a little bad behavior on Excel. I just noticed when I do this and I try to back up, it kicks me to the top of the page. All right. So this is now what we call, instead of the average distance to the mean, we can't call that the same thing anymore. Average distance to the mean. Now we have to invent some descriptive language around here, and we're using this as a yardstick now. This has been all arbitrary. We've looked at this curve here and we said, what's a descriptor of the narrowness or wideness of this curve? And we're using this yardstick, and we're going to call it the standard. Okay, so everybody back up here. Everybody take a deep breath, because we're going to put the word standard in here. This is an acceptable across the board at all conferences. This is the standard deviation, and that should give us the idea of a difference here. What's the standard deviation? It's like the average distance to the mean, right? Standard deviation. They had to create new words because it wasn't just a simple case anymore. These words reflect a simpler case. The standard deviation has the complexity of a square and a square root. And that's the story of statistics. And that's where we need to get to with this. So if you understand this to this point, you might have to go over it a few times. You might have to come back later on. But truly, if you want to understand why we use this, how we use it, it pops up in a lot of other things like psychology and sociology and in natural sciences, things out in the real world with science. For instance, our department here, science department, Evan goes out and he studies viruses. So he studies virus out there, and I'm sure at the basis of what he's doing counts, and he's modeling the data, and he's using standard deviation in here. It's really the core, the beginning of all statistics, and it's as far as we really go here. And my next video will take us into chapter 3, where we use it for chapter 3. the last step, the mechanics that we need to go through here, is just compare the simple version that lasted for many years with the cave people of average distance to the mean, and we ended up with an average of 53.8. It's our x bar. And we ended up with the ADTM 4.1. So remember, this is a lot smaller than our average, okay? It doesn't mean anything. In this case, that's just the case. It doesn't mean anything. But in our case, that the average was at 53.8, that 4.1 can be plotted here, okay? So if this is the mean up here, x bar, right, we can come up here 4.1 degrees Fahrenheit, and that's just an arbitrary yardstick that we said. 4.1 is the yardstick for our data. It says the average distance to the mean is 4.1. If the data were different, it might be tighter like this. What would our standard deviation be? The average distance to the mean would be smaller, and it might be 3.2. For another locale, if we're taking temperature data, you were on an island and somewhere else, like I'm thinking maybe southeast Florida, Miami, Coral Gables area, where they might have more tropical weather down there that's steadier. Okay, it's just a hunch, I don't know. But different data will have a different average distance to the mean of all the data. And if it's closer to the average, it's going to be a smaller average distance to the mean. Okay, so now we're going to go forward with what we now know, that we're going to have to use a more sophisticated model of this so that whatever we work on can be appreciated further on down the line. Other people can use it. Okay, we're going to use a standard deviation. I want to show you the difference between that. Okay, so if you remember, we got these absolute values of all those distances, and down at the bottom we did an average of all those. That's the simple cave person approach to things. You could actually use that, but people don't. Okay, so don't get me wrong, I'm using this as a learning tool here and a progressive lesson as to how things really work. Okay, so I think I need another column or two here, so I'm going to right click that and insert and do a Control Y, give myself at least those two. They don't have to be that big yet. Probably will never have to be that big. But now we're going to use the definition of standard deviation, remember? So we have standard deviation is equal to what? It's equal to the square root of x of I. I'm sorry, let's back up there for a second. It's a sum. I have to fit that underneath there, so I better get it. Of x of I, that's x of I minus the average squared everything over n. So this, make sure you get that underneath there. And so it misbehaves a little bit. Where we're headed with this, though the math works, all you do in math is now you appreciate as you go forward. We've had to arbitrarily adjust our understanding and definition of the width yardstick here to be this. Okay? So it's a little bit complicated, where we take that distance, we square it, then we take the sum of all those distances, we divide by the number of points. That becomes the average squared distance of all the points to the mean. And we take the square root of that to bring it back down again. And what's happening is our little n never got squared, and what happens is that causes an effect here on the eventual data that we get. Okay? So there's our equation. All right, so what we can now do is take the distance to this mean. We're going to use this column here because we have the distance to the mean of all the points, and we're going to square it. I'm going to say d. I'm not sure if this will work, so I have to do d raised to the 2, which is squared. Okay. So when you put a little single apostrophe, the cell knows to interpret that as just text. It just puts in there what you put in there. So this is going to be our distance squared, and that's just going to be the distance there, actually squared. Okay, and you can see these numbers are pretty big. So remember, let's look at where the average is. Okay, so these are These are the distances. You're going to notice something that, if you're far away from the mean, remember this is the distance to the mean, so if you're far away from the mean, the numbers, because they get squared, get big. They get big pretty quickly to the square. Okay? And as you get down toward the center area around the mean, so around our mean was 53. We're not quite there on my list yet. So the mean is 53.8. And what we're going to do is I'm just going to highlight this as the middle of the table. So these were the numbers that are sitting, the actual numbers we took that sit right at the mean. It's coincidental, but you take into consideration all the points and do their average. They came out, and year 4 and year 23 happened to have exactly the mean as the data for that day. It's just a coincidence. Okay, so we squared all those distances, right? What's the next step? So we have to sum all of that to get an average. Okay, so we're going to come down here. If you go by the equation, come down here, we're going to add it all up. I'll just use the formula, auto sum, and it should grab the whole column, and we get that. Okay, so what was the total sum? The sum of all the distances squared were 5,092.45. Okay, and we're going to hand calculate the average now. So it's going to be that number over 200. Okay, so we're going by the equation 25.46. I'm going to name that as average dot d2. That's d squared. Average of the distance squared. We'll even paint it here. How about we paint it yellow? Because it was a conclusive line there. If you want to add a little formatting, double lines don't hurt. There. So we can tell the data from the summations down here. Save my file off. Okay. So what we just did was we summed all these distances squared and we divided by n, and now we just have to take the square root and we have the standard deviation. So we'll come back down here, and this is going to equal the square root of this. So you can use a square root of that number. The square root of that number is 5.05. Okay, so we're going to round that. 5.05. Hang on to that number. Let's come back up here. So 5.05 is the actual standard deviation. Is this below it? And we're going to paint it yellow. Okay. Now what was our other number? Our other number was 4.1. The average distance to the mean was 4.1. And something's happened here. You really want to pay attention. If we're playing with numbers, and that's what math is about, is to see how things behave and see that the equations, see how they work, push on it a little bit, move it a little bit, see what happens here. Let me just paint that up a little bit. There we go, highlighted it, flooded it. Okay. What you're going to notice is because of the fact that the n sits underneath the square root sign, there is an effect of square rooting n in this version of what we're looking for that doesn't happen in the average distance to the mean, correct? Okay, because if I write up what's the equation for average distance to the mean, let's look at them. Equals 1 to n of the absolute value of x of I minus the mean over n. We had no square root in here. Because we need to do some square root along the way to get this back home again, these numbers get too big, so we have to bring it back to square root. Treat the numbers in their native format or their native units. That this n has the effect when you do the standard deviation of having its square rooting effect in here where it doesn't here. And when you have a number in the denominator, you know when that starts getting smaller, the overall fraction gets larger and larger, and that's why the standard deviation will always be bigger than the ADTM. Okay? So the ADTM was a learning instrument or vehicle or construct. I use the average distance to the mean to get the idea that we're setting up for some number that expresses the average distance to the mean, and the only aberration that occurs is we had to take the simple equation and manipulate it so math could progress. Truly, I mean, that's why it even looks like this. And I don't think anybody or too many people teach that the origins of this, the motivations of this will help you remember why you're doing what you're doing in here, and you are reminded why there's a compromise. In order for us to advance the world of statistics and understanding probability and such, we had to do it this way because the math works out, literally. And so there's an arbitrary compromise in the way that we write this up. So everybody gets thrown off by the square root and the sum sign, this sigma, uppercase sigma sign, and a square, and okay. And that's what I'm trying to help you with, is remember what the basic motivation was here, and we just had to go here. It's just the way that it works. So hopefully you're able to take a table of numbers now and actually compute the standard deviation. And in worst case scenario, if you can't get the standard deviation, go back to what the concept was and say, what's the average distance to the mean? You just won't be understood in the rest of the world. Okay, so I'm not teaching this as a technique that you're going to go out and use in your work spot. It's, again, a learning instrument to get us to the standard deviation. It's just a historical motivation of why we ever end up with a standard deviation. And of course, the standard deviation, the symbol for that is lower sigma. Okay, so we have little sigma here. That's the upper sigma. I hope this helps. And you can go back to this innumerable times if you really want to understand where we get to, because the next path gets more complicated. Now we start using this in distinctly two different ways in the rest of the operations course.